We are asked, given the plane f of x comma y equals 1 plus 2x plus 3y, to parameterize the plane and find the area over this region. A great first step would be to visualize it and to just draw it out. Here we already have our x-axis, our y-axis, and our z-axis. So looking ahead, I think it would be a good idea to draw the plane over this region. So let's first draw out the region on the xy plane. This just means that x goes from 0 to 3 and y goes from 0 to 2. So 0, 0, x will go from 0, let's say right here, and y will go from, to say around here. And then we have to draw out the parallel lines, and here's our region. Right? And now we want to draw the plane itself. So let's go ahead and plug in some points so we have a better idea of what this is going to look like. So naturally we would use the corners of the box. Let's start out with the origin because that's really easy. Right over here. So at the origin, or above the origin, the height of the plane is just 1. So here we have our first point, 0, 0, 1. What about at this corner? Here x is 0, and the y value is 2. So we want to take f of 0, 2, which equals 1 plus and we have another point. X is 0, y is 2, z is 7. Okay. And finally, above this corner, where y is 0 and x is 3. So f of 3, 0 equals 1 plus 2 plus 3. Which is also 7. And we have our final point, 3, 0, 7. And let's draw these out. First, above the origin, go over about 1. And above these 2 points, we go up 7. So let's just say somewhere around here. And if we connect we're starting to get a better idea of what our plane will look like. Now once again, looking forward, we want the area of the plane over this specific region, and since the region is rectangular, due to the properties of the plane, the piece of the plane is going to be a parallelogram. So to finish drawing out the piece of the plane, we can just draw parallel lines to these lines which we already drew along the plane. So just draw one parallel to this, and one parallel to this, as such. And if we connect everything up, this will actually be above this point. And now we're starting to see what it's going to look like. We have the plane back here, and we have kind of almost a prism formed underneath it. So when we're thinking about parameterizing a plane, what we need is a starting point and 2 vectors. Whenever you parameterize a surface, because it's going to be 2-dimensional physically, you're going to need 2 parameters. And what will we do with these 2 parameters? Well, if you notice, above the origin, here we have a point, and we've sort of drawn out a vector. above this corner and above this corner. And these are the borders of the parallelogram that comprises the piece of the plane that we're dealing with. Let's first consider this line. If we were to parameterize this, we would start out here physically, and the parameter would draw out this line. Now, if we already have this drawn out and we introduce a second parameter along this line, this would drag the line across and draw a plane. So how could we numerically represent this? Well, let's first find the values of these vectors. We know this point, we know this point, and we know this point, so this should be relatively simple. The first one I'll call D1, will be from here to here. And we just want to take the difference between the vector representation of this point and this point. This point, as we saw earlier, is 0, 2, 7. And the other point is 0, 0, 1. And when we subtract them, we just subtract each individual component, and we end up with 0, 2, 6. Similarly for D2, we start out at this point, which was 3, 0, 7, and we subtract the same vector, which is the starting point, and this will give us 3, 0, 6. So now we have two vectors that both lie on the plane. If we start out at this point, right? And now we can introduce the parameters for the first time. Let's call the surface, when we parameterize it, we typically like to use R, and you can name it anything, but it does have to be a vector, right? Of these two variables. These are our two parameters, u and v. You can use anything else if you'd like. And remember, we want to draw out the line with one parameter and drag it across with the other. So we start out with the starting point, and then we can draw out the line with one parameter along here, so plus D1 times first parameter, and then after this we drag the line with the other parameter. And if we write this out fully, we get and right now we could say that we're done because we do have a vector equation and it's in terms of two parameters. But a lot of times when we parameterize curves, we're going to want it in the form of x of u comma v, y of u comma v, and z of u comma v. And to go from this to that is really easy because in each of these terms we have an x component, a y component, and a z component. So if we write that out as a single vector, by adding all the components of these, we will get 0 plus 0u v, zero plus 2u plus 0v, and finally 1 plus 6u plus 6v. And this simplifies down to and we're done. We've parameterized our plane. So now let's move on to the next step. Find the area over that region. Well, let's take another look. If you remember, we were thinking about this region, the parameterization, in terms of these two vectors that go along the boundaries of the parallelogram. And it turns out that one property of the cross product is the magnitude of the cross product of two vectors will give us the area of the parallelogram formed by them. If we were to draw that out, if we have these two vectors, A and B, the magnitude of A cross B equals the area of this parallelogram. Well, we already have these two vectors we found earlier, and they form this parallelogram. Now we just need to take the cross product and find the magnitude of that. So our two vectors are 0, 2, 6, and we want to cross that with 3, 0, 6. And this equals we can just proceed with taking the cross product normally. Cross out this column, 12 minus 6k, or 6i, so that would be I plus minus 0 minus 18j plus out the third column, 0 minus 6. Check the first one. 12 minus 6. Oh, minus 0. Okay. My bad. And this simplifies to 12i plus 18j minus 6k, which we can just write as and here's our cross product. Now all we need to do is find the magnitude of this. But before we go ahead and do that, we want to double check to make sure that this is perpendicular, that this is a normal vector to our plane. And one thing we can reference is the original Cartesian equation of the plane we're given, because this gives us information about a normal vector. If we write it out in terms of z instead, we get z equals 1 plus 2x plus 3y. And if we move the z to this side, we get 0 equals 1 plus 2x plus 3y minus z. And this tells us that a normal vector to this plane should be a multiple of the coefficients of each of these variables as components of a vector. So 2, 3, negative 1. And if we double check over here, well, it looks like if you multiply that whole thing by 6, 2 times 6, 12. 3 times 6, 18. Negative 1 times 6, negative 6. So it looks like this is a normal vector, and we did the cross product right. And all that's left is to take the magnitude of this. To do that, we square all of the components, add them together, take the square root. So, I want the square root of 12 squared plus 18 squared plus negative 6 squared on, wait, and instead of doing this fully, what we could do is just take the magnitude of that and multiply it by our multiplier, which we found earlier to be 6, equals 6 times the magnitude of that vector over there. 2 squared plus 3 squared plus 1 squared, which is 4 plus 9 plus 1, which is 14. And that's our answer.